The James Webb Space Telescope is more than just a telescope, it's a highly specialized research lab, investigator, and vast detective all in one. It allows us to gather accurate and reliable data about a world we've never visited. The story takes an unexpected turn, just like in any science fiction thriller. Scientists using the James Webb Space Telescope received something surprising from Proxima b, a signal so astonishing that it spread throughout academic halls and social media. Named as a potential techno-signature, it was an electromagnetic discharge so complex that it defied natural explanations. Unlike random cosmic noise or the predictable emissions from stars and planets, this signal carried patterns, structured, repeating sequences that hinted at intentional design. At first, skepticism ran high. Could it be an artifact of the telescope itself? A misinterpretation of background radiation? Scientists at institutions worldwide scrambled to verify the data, cross-checking it with other observatories. But as the days passed, the evidence only grew stronger. The signal wasn't from Earth, and it wasn't a known astrophysical phenomenon. Then came the real shock. Hidden within the transmission was a sequence of prime numbers, a universal constant in mathematics, often considered a potential marker of intelligent communication. If nature doesn't count, then something, or someone, was doing the counting. Now, the world watches as researchers attempt to decipher the full message. What is Proxima b trying to tell us? And more importantly, who is sending it? Promised to reshape our view of reality, could the signal be the actual proof that we are not alone in the universe? And just as quickly as it appeared, the signal disappeared without repeating, leaving behind not just a stunning silence but also a maze of unanswered questions and bubbling hypotheses. Was it simply a transient cosmic anomaly, a random event of infinite arrangement, or something else, intentional? A coded message? Or even a sign of extraterrestrial intelligence? The solitary mission cast a lingering remnant of mystery over Proxima b, sparking wild discussion and speculation. Was it just a passing oddity, or is it part of a much bigger story, more perplexing than we can imagine? But wait, the tale of our cosmic exploration is far from over. The ink has not yet dried, and new chapters are still being written. This time, it's not just conventional specialists but Harvard researchers who are leading a shift in perspective. As we continue the search for extraterrestrial life, they are not satisfied with merely studying the signals and anomalies we've discussed so far. They're upping the ante by turning the James Webb Space Telescope into a kind of giant night vision telescope. They plan to search for artificial light sources in both the dark and illuminated areas of distant worlds. We're looking at staggering possibilities, such as the chance of detecting artificial versions of cities, glowing in the dark like brilliant specks. Imagine seeing glowing light emissions. It could be a city humming with the presence of an advanced civilization, transmitting its glow into the vast, vast oceans. As we continue to unravel the secrets of the universe, the quest for extraterrestrial life takes on new aspects beyond the immediate interest in Proxima b. Our grand pursuit digs deeper into the vast new regions of space. This pursuit is driven by both technological advancements and a profound desire to understand our place in the universe. Advances in cosmology and space exploration have led to the discovery of various exoplanets with potential habitability. Instruments like the James Webb Space Telescope, biosignatures, and ground-based observatories have expanded our ability to detect and study these distant worlds. One particularly fascinating area of study is the search for biosignatures, signs of life. These signs could include atmospheric gases like methane or carbon dioxide, which, under the right circumstances, could suggest biological processes. The JWST's capabilities extend beyond basic discovery. Its advanced instruments can measure the atmospheric composition of exoplanets with remarkable precision. By studying starlight that filters through an exoplanet's atmosphere, scientists can identify chemical markers characteristic of life. For example, the presence of water vapor alongside other molecules such as oxygen or ozone could point to the potential for life-sustaining conditions. Another avenue of investigation involves studying the conditions of these distant worlds. Atmospheric models based on data from the JWST can help predict whether an exoplanet's conditions could support liquid water. This is crucial because water is considered an essential element for life as we know it. Scientists are particularly interested in planets located in the habitable zone of their parent stars, where temperatures could allow for stable liquid water. The search also extends to the moons of exoplanets. Some of these moons, especially those in the habitable zones of their host planets, could have conditions conducive to life. For example, icy moons in our own solar system, like Europa and Enceladus, are thought to harbor subsurface oceans beneath their icy crusts. Similarly, moons orbiting exoplanets could present similar conditions where life could exist. Additionally, the concept of technosignatures has gained momentum. These are signs of advanced civilizations that may be detectable through artificial structures or technologies. This could include megastructures like Dyson spheres, speculative constructs designed to capture a star's energy, or unusual patterns in radio transmissions. As we refine our global collaborations and observational strategies, the search for technosignatures could reveal the presence of extraterrestrial intelligence. In addition to technological advances, global cooperation plays a critical role in the search for extraterrestrial life. Collaborations between space agencies, research institutions, and private companies enhance our ability to explore space. Missions to Mars and other celestial bodies include contributions from multiple nations, pooling resources and expertise to achieve shared goals. Public engagement and education are also vital components of this mission. The excitement surrounding space exploration inspires the next generation of scientists and engineers. Outreach programs and educational initiatives help foster an interest in STEM fields and encourage young people to pursue careers in space science. The advancement of new technologies also contributes to our understanding of the universe. Progress in telescope design, data processing, and computational models improves our ability to detect and analyze distant exoplanets. For instance, upcoming space telescopes, like the planned Extremely Large Telescope, ELT, and the Habitable Exoplanet Observatory, HABEX, are poised to provide even more detailed observations and deeper insights into the potential habitability of exoplanets. As we push the limits of our knowledge, each new discovery raises new questions and areas for exploration. The search for extraterrestrial life is not just about finding alien civilizations, it's also about understanding the origins and potential diversity of life in the universe. It challenges our understanding and broadens our interpretation of what it means to be alive. In conclusion, the exploration of exoplanets and the search for extraterrestrial life are dynamic and evolving fields. With each step we take, we edge closer to answering some of the most significant questions humanity has ever asked. As we continue to explore the universe, the opportunities for finding new forms of life, and understanding our place in the cosmos, remain boundless. As our technological capabilities grow, so does our ability to refine the search for life beyond Earth. The next generation of space missions is poised to answer questions that once seemed beyond our reach. One of the most anticipated missions is NASA's Habitable Worlds Observatory, HWO, designed to take direct images of Earth-like exoplanets in the habitable zones of their stars. Unlike previous telescopes that primarily detect exoplanets through indirect methods, such as observing how they dim their parent star's light, the HWO aims to capture detailed images that could reveal surface features, weather patterns, and even potential biosignatures. Meanwhile, private space companies are entering the search for extraterrestrial life with ambitious projects of their own. Organizations like SpaceX, Blue Origin, and Breakthrough Initiatives are developing advanced propulsion systems that could one day allow for interstellar probes capable of reaching nearby exoplanetary systems. The Breakthrough Starshot project, for example, envisions a fleet of ultralight spacecraft propelled by laser beams, capable of traveling at a significant fraction of the speed of light. If successful, such a mission could reach Proxima Centauri b, one of the most promising exoplanets, within a human lifetime. Beyond exoplanets, new interest has emerged in exploring the subsurface oceans of icy moons within our own solar system. Future missions, such as NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, will investigate the potential habitability of moons like Europa and Ganymede, where vast oceans beneath thick ice sheets could harbor alien microbial life. Some scientists even propose sending robotic submarines to drill through the ice and explore these hidden oceans firsthand. At the same time, astronomers are refining their methods for detecting extraterrestrial megastructures, hypothetical large-scale constructions built by advanced civilizations. The idea of Dyson spheres, structures that could encompass an entire star to capture its energy, has led scientists to analyze unusual light curves from distant stars. While no confirmed evidence of such structures has been found, the search continues, driven by the possibility that civilizations far more advanced than ours might have left detectable footprints in the cosmos. The study of exoplanet atmospheres has also taken a giant leap forward. Scientists are now exploring not just the presence of gases like oxygen and methane but also the possibility of detecting industrial pollutants, a potential sign of an advanced alien civilization. If an exoplanet's atmosphere contains complex chemicals that do not occur naturally, it could suggest technological activity. With each breakthrough, our view of the universe continues to evolve. The once unthinkable idea that Earth is the only planet harboring life is being challenged by new discoveries, leading us closer to an answer that could redefine our understanding of existence. The search for extraterrestrial life is not just a scientific endeavor, it is a profound exploration of who we are and what our place in the universe truly means. Whether we find evidence of life on a distant exoplanet, in the icy oceans of a nearby moon, or through the faint whisper of an alien signal, one thing remains certain: the journey has only just begun.